morning to you, my dear students and all followers of this program. This very important academic program. I want to welcome you this morning. Teacher Kakuli is my name, and I am here to take you through Physics 2, A-level. I want to thank God for the activities that we have all gone through during the week, and continue to pray that God keeps us well. To the candidates out there, Senior 4, Senior 6, continue reading. Continue reading. One writer said that if you want to keep yourself warm, you must chop your wood to the size you want. I want to encourage the candidates following this lesson and attending this program right away to keep chopping their own wood so that they can eventually enjoy success when they eventually get good results. We shall start with a few examples that are already on board. I'll request that you capture them. We shall start with number 1. Number 1 says that an object is 10 centimeters from a convex mirror. It is a basic, simple question. What distinguishes this question from an O-level question is that at A-level we don't have accurate scale drawing, and therefore we must use the formula. At O-level, the formula is not encouraged, and therefore students must use accurate scale drawing to find whatever is required. An object is 10 centimeters from a convex mirror. The key points here are convex mirror. We already looked at that for a convex mirror, the focal length is negative. In other words, the principal focus is virtual. So we shall consider for our solution that we have been given an object whose symbol we use U, and U is 10 centimeters, and the mirror is convex. They are saying if the mirror has a focal length of 15, since the mirror is convex, the focal length must be negative 15 centimeters. They want us to find the position of the image. So it is a basic question, and we must state the formula we are going to use. Using 1 over U plus 1 over V is equal to 1 over F, then we can substitute and get our 1 over 10 plus 1 over negative 15 should be equal to 1 over F, because we are looking for, we are looking for V should be equal to 1 over negative 15. So when we make V the subject, our 1 over V will be 1 over negative 15 minus 1 over 10. And this, if we take the LCM on the other side, the LCM will definitely be 30 for 15 and 10. If we take 30, this is negative 2 minus negative 3. So this implies that our negative 5V is equal to 30, implying that therefore the V is negative 6 centimeters. So we can say that the image is 6 centimeters behind the mirror. Remember that convex mirrors form virtual images. They form virtual images, and therefore, if the image is formed and is virtual, it is going to be behind the mirror usually. And we saw the properties of this image, that the image is upright, it is virtual, it is diminished, and it is formed between the focal point and the pole of that mirror. Very simple basic question. Students are encouraged to remember to attach the right units and to do the mathematics very well. We can move on to our second number. I want to continue to encourage students to copy these questions. If they cannot copy fast enough, I will not forget to remind you to ensure that you take a quick picture. Question 2. These questions will give us skills on how to interpret these numbers. I noticed we need to do a little more numbers before we look at the focal length experiments. A mirror forms an erect image 30 centimeters from the object. 30 centimeters from the object, and twice its height. Now, that means that I can pick, if they are saying twice, that is the magnification. The magnification is 2, and we are aware that magnification M is V over U. We shall let object, the object distance be U. If we let the object distance be U, we can use this formula in this magnification to find the image distance. So using our 2 now, which is the magnification, to be equal to V over U, it implies that we can get our image distance in terms of the object distance. The V can be got as 2U. Now when I go back, they are saying a mirror forms an erect image. The image is erect, and it is magnified. The image is erect and it is magnified. And its height is twice the object. And the image is 30 centimeters away from the object. This implies, the 30 centimeters from the object implies that the object distance plus the image distance should give us a total of 30. But we already have V in terms of U, so it means we can say U plus 2U will be equal to 30, and therefore 3U will be equal to 30, and therefore the object is actually 10 centimeters. Is actually 10 centimeters from the mirror. They want us to find where must the mirror be situated. The object is 10 centimeters from the mirror. Where must the mirror be situated? We will answer that when we determine what the radius of curvature is. Now that we have U, it implies that the V is also known. 2 times 10, which is 20 centimeters. We have U and V already, and therefore we can go ahead and determine the radius of curvature. If we determine the radius of curvature, then we can tell that the mirror is situated at a distance of the radius of curvature, or we can say it is situated at 10 centimeters from the object position. So what we are going to do here is, I can even answer this. What is the type of the mirror? The fact that the object is erect and it is twice the height of the image, it is twice the height of the object. The fact that the image is erect, and twice the height of the object implies that this mirror must be a mirror that magnifies objects, and therefore the type of mirror, I can say the mirror type. The mirror type should be convex, since the image should be concave, since the image is magnified. It is a concave mirror. We can go ahead to find what R is. We shall use the mirror formula. 1 over U plus 1 over V is 1 over F. And we have our U. So 1 over 10 plus 1 over 20 should be equal to 1 over F. This implies that 1 over F is equal to The LCM will become 20. We have 2 plus 1. They are saying where must the mirror be situated, and we should be able to discover where it must be situated. We want to find the value of f, so how will we find the value of f? Okay, let me see. A mirror forms an erect image 30 centimeters from the object and twice its height. Where must the mirror be situated? What is the value of the radius of curvature, assuming the object is real? They are telling us this. If the object is real and the image is magnified, then this image must be negative. It must be negative. This is the situation for the candidates that are following, where the object must be between the principal focus and the pole for this mirror. And therefore, this 20 is negative. So when we take our LCM, it implies that we shall have this as a minus. And this implies, therefore, that our f will become negative. We shall have our f giving us a positive 20 centimeters by calculation. And since they want the radius is always twice the focal length, it implies that the radius of curvature is going to be 40 centimeters. The radius of curvature is going to be 40 centimeters from the pole of the mirror. Where must the mirror be situated? We can say the mirror must be situated 40 centimeters from the center of curvature. And we have said the type of the mirror is concave. The type of the mirror is concave. As you capture that number, I can erase this one here and create space for yet another number. Yes, we can now focus our attention to the current question. We can now focus our attention to the current question. Example number 3. The question says a concave mirror forms on a screen a real image that is twice the linear dimensions of the object. Once again, as we attempt to look at this, the magnification is twice the object, the linear dimensions of the object. The object and the screen are moved until the image is 3 times. So that means that we have 2 cases here. It means that we have 2 cases here. And I will consider this as case 1. For case 1, my magnification is 2. And they are saying it is moved, object and screen are moved until the image is 3 times. Until the image is 3 times the size of the object. That means in another case that we shall be seeing, the magnification is 3. If the shift of the screen is 25 centimeters, the shift of the screen means that this is the difference between the 2 image positions, case 1 and case 2. The difference between the image positions of case 1 and case 2 should be able to give us 25. They want us to determine the shift of the object and therefore the focal length. The shift of the object and the focal length. Since we have magnification, we shall use let image, in this case B, at image position B at V. So it means if we use that magnification is given by V over F minus 1, which is one of the expressions we looked at last time, our 2 should be equal to V over F minus 1, and we can call this equation A. If we go to the second case, and we let the image be at a distance that I can call V prime, it means that my 3, again using the same formula, M is V over F minus U, my 3 will be equal to V prime over the focal length of the said mirror minus 1. And this can also be labeled as equation B. This can be labeled as equation B. Since they are telling us that the shift of the screen is 25 centimeters, the shift of the screen is interpreted to be the shift in the image position. That is the shift in the image position, and therefore, if we get that difference, which should now definitely be obtained by subtracting these 2, we can say that shift in the screen should now be the same as V prime minus V. And they are saying this is 25 centimeters. So if we play around with these equations, we shall subtract. By subtracting F from B, it will give us that 3 on the left-hand side minus 2 should be equal to V prime over F minus 1 minus into V over F minus 1. If we open brackets, this will give us a 1. We shall have a v prime. If we open brackets here, we shall take away v. These are all over f. And we shall have minus 1. Minus minus will give us a positive. And therefore, our 1 would be equal to v prime minus v over f. Since v prime minus v is 25, it implies that by cross multiplication, f times 1 is equal to v prime minus v. And therefore, from here, we can get the focal length as 25 centimeters. The focal length can be obtained as 25 centimeters. But they want us to find the shift in the object. We have found the focal length. They want us to find the shift in the object. I will use a recall here. Whereas magnification has been seen as v over f minus 1, we know that using our 1 over u plus 1 over v is equal to 1 over f. For those who cannot recall, if we multiply through by u, we will get 1 plus u over v is equal to u over f. And this implies that u over v, which is 1 over m, u over v, which is 1 over m, will be equal to u over f minus 1. We looked at that formula. So I will use the same approach. Consider u to be the image position in case 1. Consider u to be the image position in case 1. If u is the image position, the object position, sorry. If u is the object position, and it would imply that my 1 over 2 would be equal to u over f minus 1. I would call this equation 1. Then in case 2, if my u is equal to object position is u prime, then we can equally get 1 out of 3 is u prime over f minus 1. And this can be our equation 2. So we can also use that expression. I will rub off the original question. I will use that expression. My intention is to find the object difference. And since a half is greater than a third, we can subtract 2 from 1. Subtracting 1 minus 2 will give us that a half minus a third will be equal to u over f minus 1 minus into u prime over f minus 1. If we take the LCM here, we shall have 6, and we shall have 3 minus 2 being equal to u minus u prime over f minus 1 minus minus 1 for purposes of showing the working. Remember, we know the value of f. Therefore, it implies that our 1 out of 6 will actually be equal to u minus u prime over 25. Note that f was obtained as 25 centimeters. since what we want is the difference in the object position, if we make it the subject, it will give us 25 out of 6. And this can be simplified further to give us 4 and 1 out of 6 centimeters. And you can conclude and mention that the object shifts. The object shift is 4 and 1 out of 6 centimeters. The object will shift through that distance for that particular number. The object shifts through that distance for that particular number. The object shifts through that distance for that particular number. You can capture that solution as we prepare to go through the next part. There are definitely several questions. As you've noted, there is an example we did last time. We have so far done 3 examples, and they are all unique. They are all unique and different. I will challenge you to look out for more. And I still have more to share with you as long as, of course, the time allows. Time, I will not forget to remind you, is the only resource that we all have in equal share. What makes it different from individuals is that finally this time is put to use differently by different individuals, irrespective of their age, their color, their size, their origin, and the food they eat. If time is not utilized well by one of the 2 people that may be doing exactly the same job, there will always be variations. I want to remind you students, a good number of students may have degenerated in their morale, but I want to keep reminding you that utilize the 24 hours we have that is deposited on our accounts every midnight very well, and you will definitely not regret. I want to assume that even the slowest student has captured this final bit of the number, and therefore remove all of it to prepare space for yet the last part. My interest is that we close our discussion on curved refraction today. So we look at the last part, where I will look at either a method or 2, methods of determining focal length. Methods of determining focal length of mirrors. What I want to emphasize here is that candidates out there, S4 and S6, should know that these methods comprise normally a number, and this number comes in paper 3, which is the practical paper. It comes in paper 3, and usually either it is a mirror, or it is a lens, or it is a glass block, or it is a glass prism. But for purposes of refraction, we are focusing on the mirror, since we have not talked about refraction. There are several methods. I'll give out all of them. One is using a concave mirror, using a convex mirror. Using a convex mirror, and a plane mirror. Using a convex mirror and a plane mirror. The other method is using a convex mirror and a converging lens. A converging lens is the one we also call a convex lens. The other method is using an illuminated object that is placed at the center of curvature. At the center of curvature. Of course, it is discovered later that it is placed at the center of curvature. And with the help of a concave mirror now. In other words, the mirror used there is concave. And the other method is using the no parallax method. Using the no parallax method with a search pin and a search object. And a concave mirror also. This last method is popularly referred to as the object image distance method. The object image distance method. I would like us to look at that first method where we are saying we are using a convex mirror and a plane mirror. But these are all methods that can be used. So we shall look at that one. And we begin with a diagram. The candidate is expected to draw a correct diagram here. Since we are using a convex mirror and a plane mirror, we can consider that to represent our convex mirror, which we are going to label. Of course, the mirror is always placed in a mirror holder. And we shall have a plane mirror that is just half the size of the object. And the plane mirror is going to face the object. The object is used in such a way that it is cutting across the principal axis. Since we know originally the object is used, the upper part of the object. This is going to be our object. I'll call it O. This is going to be our mirror. And I will call this our convex mirror. This object, through this mirror, will form a virtual image, which we can put like that. By default, all of you know that convex mirrors form virtual images. But this part of the object that is in front of this mirror, if I let it be at a distance y away from the mirror, from the properties of plane mirror image formation, the object distance is the same as the image distance. For purposes of, okay, I will not rub off, but I will say it is not drawn to scale. Not that the diagram is not drawn to scale, but for purposes of the explanation, this object distance, maybe I can shift this a little. It is so near, I can shift it a little so that there is some justification here. If we let the object be a distance y from this plane mirror, this plane mirror is going to be moved. I will put the highlights of the steps. The explanation is that the object O gives us a mirror through the convex mirror, which gives us an image through the convex mirror here. But the plane mirror is then later introduced. It is moved to and fro until when this portion of the object, the image of this portion of the object, coincides with the position of the image right over here. Coincides with the initial position of the image through the convex mirror. And when that happens, then these distances, I will use this as x, because they are now fixed. These distances of the object from the mirror, the convex mirror, and the object from the plane mirror can then be measured. I'm assuming that I've measured them and given them x and y, but practically they will be measured and you have their values recorded to one decimal place, remember. And from the principle of reflection, as I was explaining through plane mirrors, it implies that this distance is also equal to y. We clearly saw that at the very start of the discussion of this topic, that images formed through plane mirrors have several properties, and one of them was that the image distance behind the mirror is equal to the object distance behind the mirror. Why is the image virtual? Because this type of mirror forms a virtual image, and similarly this type of mirror forms a virtual image. Now, if we call this I, and I think, yeah, if we have those different labels, we can say the interest is to determine the focal length of this mirror. So I want to repeat that the object O is pressed at a known distance x. The object is pressed at a known distance x. From the convex mirror, and its image is obtained at a position I. A plane mirror M is then introduced between O, I'm referring to O as the object, and C facing the object. Facing the object implies that the reflecting surface of the plane mirror is facing the object. It is then moved to and fro. It is moved to and fro. The plane mirror is the one moved to and fro until when its image coincides with the image formed through the convex mirror at position which I have called I. This process is by no parallax. By no parallax. Distances x and y are then measured and recorded. In physics, when we measure, we record. And what happens next is, how do we then use these distances to determine our focal length? How do we use these distances to determine our focal length? We are looking for the focal length of the mirror and the mirror is convex. So the object distance which we normally call u is x from the mirror. And the image distance from the mirror is this. Let me call it v. The image distance v is what we want. How do we get v? We can say that v will be obtained from OI. If we get OI and we take away OC, we get V. OI minus OC, OI minus OC is V. But note that V is negative. So it implies that V is going to be minus. Our OI is Y is 2y, and our OC is x. And therefore, using that 1 over u plus 1 over v is equal to 1 over f, 1 over f will be equal to 1 over y, 1 over u, which is x, plus 1 over v, which is our minus 2y minus x. This formula can therefore be used to determine the focal length since x and y were measured and are known. This formula is therefore used to determine x and y since they were measured and known distances. Since they were measured and known distances. Yeah, our V is CI, and CI can be obtained as that. I hope you are capturing that. And as we move to the last bit of our lesson, I would wish that we try out an example, and I will make it a summarized example. We will try out an example before we close this lesson. One thing that candidates should note here is that the plane mirror that we have labeled M should be just enough to cover half of the curved mirror C. It should just be a half or a small mirror that can cover a half of this. And the point C is assumed to be the center of the aperture of the convex mirror. So I can clear off this explanation. We'll request that if you are still capturing it, you can capture. And also emphasize that most of these diagrams may not easily be found in an Elcon. So candidates should take note. Maybe senior 5 students and some S6 students, because various schools begin teaching from different sections. As I told you, this paper has different sections. So there could be some senior 6s that have actually not covered this. You must take the opportunity when it still counts. Take a picture. I'm going to rub off from here, given that by convenience it is easier to start writing from the left to the right, since I am right-handed. So I'll clear off this part. I will put an example question with only diagram. With only diagram that is typical of what you have, what is still actual on the board. If I have a diagram of this nature, and I have an object, and I have a mirror over here, and they are given that this is 20 centimeters, which we said is the object distance, and they are also given that this is 15 centimeters, you are asked this is the image, and we want to find its distance. They say if u is 20 centimeters, and object O is 15 centimeters from the plane mirror, determine the focal length of the convex mirror. I have summarized that question so that it can suit in the available time. Otherwise, the descriptions would be an object O placed 20 centimeters in front of this, forms an image. When a plane mirror is brought 15 centimeters from there, it forms an image which coincides with the image through the convex mirror at I, determined given these values. So we shall say that our U, from what we have just discovered, our U is 20 centimeters. And since this is a plane mirror, using the plane mirror image property formation, this will also be 15. So it implies that our V is going to be 30, which is 15 plus 15 minus 20. And remember that I have said that it is a negative distance. Therefore, our V is negative 10 centimeters. And therefore, using the formula, using 1 over U plus 1 over V is 1 over F, we can find F as 1 out of 20 plus minus 1 out of 10, which implies that we shall get 1 minus 2 out of 20, and this will give us our F as negative 20. This implies that our f will be negative 20 centimeters. Our f will be negative 20 centimeters if you calculate. So they can give you a question of that nature, and you should be able to use that knowledge to find the image. I can give you an exercise in the remaining 4 minutes. Exercise the question is there, and candidates, please take the photo. Determine the focal length. Determine the focal length. They are saying complete that ray diagram if the object is 20 centimeters and the pole of the mirror M2 is the center at the same time. Draw a ray diagram, show successive reflections, and use the ray diagram to determine the focal length. I want to thank you so much for attending the lesson and wish you a very nice weekend. Continue reading. God bless you.